Let's consider a PMOS transistor, and it works the exact opposite way as an NMOS transistor works. In that we have a big, I shouldn't say big, really these transistors can be very, very, very small. But we've got an N type semiconductor here, so it's doped with something that makes it have an abundance of electrons, and then that means that we've got two other zones that are doped to be p-type, where it's got a excess of holes or positive charges. And we still have this insulating channel that we put on here. And we've got a plate, and we've also got some plates there that are also conductors. And now, just for real quick, our terminology, we've got, this is still our gate, and we'll call this our drain, and this our source. So this time we go plus to minus that way. And so this still has the same phenomena as the NMOS, where we've got these kind of barriers built up here. And so that makes things impossible to flow across here. Given the right conditions, given these right G conditions. So let's look at that. Actually, let's make a table here. So we're going to say gate, and we'll consider our current. So if our gate is a 0, what that means is we've got an excess of electrons here. Right? We've got an excess of electrons. And remember here we've also got electrons. And so what's going to happen is this excess of electrons is going to push the electrons away. It's going to kind of repel them. Same as the ones in these barriers here is going to repel these downward. And what will happen is we'll end up with a channel that current can flow across. So that means when we have 0, current flows. Now, if we instead change this to a 1, where we have a bunch of positive charge here now, these pluses are going to attract these minuses. So we're going to have a bunch of minuses here, and we're going to build up these barriers on the edge, and current will not be able to flow through these barriers. So if we just say 5 volts, or remember this is kind of a minus or plus, then we have no flow. So we can look at this as a switch, right? So our switch here, we've got current flowing. That means we've got a closed switch. Something's connecting these 2 points. But if we have no flow, that means it's an open switch. And our symbol, real quick, let's think about this in comparison to the NMOS transistor. So I realize now I did my table upside down. I should have did them 5 volts or 0 or the same. But either way, this acts the exact opposite way of the NMOS transistor. So if we apply a 0, current will flow. If we apply 5, current will not flow. So Since this acts the exact opposite way of the NMOS transistor, let's first look at the symbol here. Let's draw an NMOS transistor. So we've got this guy. This is still the source. This is still the drain. And we've got this guy here. Oops, sorry. Skipped a step here. This is our gate. And so this is our NMOS transistor. But in this case, it acts the exact opposite way. And so actually, we kind of take a hint from our stuff that we know from digital logic, where if we draw a bubble here, that means the signal coming in here gets inverted. So it's like, kind of like this. We've got an inverter that then connects to an NMOS transistor. You got an inverter that's inverting the signal, so if you got a 1 here, that means you get a 0 here, and then it just works like an NMOS. But we collapse that all to make our PMOS transistor, and that indicates this sort of behavior.